cavities that these are tuning benches. Essentially what we do is we tune each one of these cells individually. And once you put a helium vessel on, you don't have the ability to do that anymore. So you really don't want to disturb that final tuning process with the helium vessel installation.
So you figured that if you weld it after, you do the tuning here?
Yes.
And then you weld it afterwards, it would take it so far out of tune that you won't be able to...
It may. I'm just simply saying, I mean, everything is process dependent.
Right,
but by having that convoluted bellows in there, it helps really isolate the helium vessel from the cavity.
Yeah. And this is your setup for it?
This is one of our tuning benches. We have two of them on the one behind you.
Oh, I see. Oh, I see. That's nice.
Coupon for don't work. That accommodates the, and they got a second bellows here.
Second bellows. Yeah, so
that accommodates the differential movement between the two shafts.
Essentially, it's just standing there, being held, nothing else. That's what I thought. Yeah. Okay, good, good.
All the way through,
okay, that was my main, That's pretty flexible. But it has to be.
It has to be for our design, like I said, to accommodate for the cool down contractions when the modules cool down.
That's right.
Okay, so all four cavities move to the center. So this is the anchor point.
That's the anchor point right there.
Yes.
As it cools down.
From an axial standpoint. So so we have a bellows in our warm to cold transition at the end of the cryomodules that simply takes up all that thermal contraction.
Right. Okay. And there's no sideways motion. Basically, you've got everything strung out on...
yes, well, they're nitronic rods, which are basically high tensile steel strength rods. That's essentially how we have our alignment house also locked in place.
Right.
So that the beam line stays in its final configuration. We do a precision alignment. It wouldn't stay that way the whole time through cool down and through the rest of the build out process. So we have high strength steel rods we use for alignment. And
you don't mind?
high strength steel rods we use for the alignment of all the cavities. That's done at the space frame stage. Then it goes into the vacuum vessel. We finish out the cryogenic end can installation.
Right.
And then it goes through its cool down process. And ideally you want to keep everything concentrically aligned as it was when it was done during the assembly.
And it does that, eh?
Yes.
It keeps everything aligned. Yeah. You preload it, and you don't have to worry about any sideways motions.
No, it's pretty much locked in radially.
Yeah.
The only motion afterwards is axially, and that's to accommodate both thermal contraction during cool down and also tuning. So when you tune these cavities, our design on this particular cryo module does not have any beamline bellows.
Right.
So when I tune this cavity, I pull all the rest of them with it.
Right.
So
I see.
But we limit that by anchoring it in the center.
Yeah.
So now you only have communication between four cavities.
That's right.
So essentially, but when we tune, then when you set up the cavities and the tuner stacks and your warm to cold transition, you need to account for all of that axial travel.
I see. And what's the maximum deflection at the end when you're cold?
By the time it's took from one extreme to the other, we have 3 bellows cartridges in there, and the design axial max is a 1/2 inch, 5/8 of an inch between.
That's pretty good.
Between the thermal contraction and the maximum tuning. So if you took everything to its extreme, that's how much it would have to accommodate.
I see. So
that's the worst case scenario if you had to tune everything in the same direction and all the thermal.
And that's why you have these guys here, so that once it's thermalized, then what do you have these things for?
So what this does, this is actually a positioning plate.
Yeah.
The opening here is largest. What this does, we can get that position so that you have that flexibility, because the cavities, when you put them together in a cavity string, are not always going to be exactly lined up with these stacks.
That's true.
So we have some clearance in there, and essentially this is a vacuum seal, and this gives you the ability to put that plate exactly where you need it.
Slides around, yeah.
Yes.
Perfect. Yeah, that's what I found. Okay. Very good.
This is the vacuum screws here to put the plate where you need it.
Yeah. Okay. Is there a central, I can't remember, was there a central strong back of some sort? Or is it all to do with the plate?
There is a space frame, which is the supporting structure inside. I don't think I have any of those sitting around right now.
Okay, sure.
But inside the vacuum vessel is the support structure, which is the space frame. Essentially, it's a tube and ring structure that is essentially the strong back that supports the entire cavity string. That's what the nitronic rods are connected to.
Right,
That's
the strong back itself. Right, okay. So it's a concentric kind of a setup.
Essentially, there's 4 tubes that run down the length of the module that are connected through rings, steel rings. Essentially, that's the whole support structure.
Right.
And they are anchored up. So the 4 tubes to go down the whole length of the module. That's what your nitronic rods can connect to. We essentially have a double 4 nitronic rod structure. That basically what gives us our alignment up the beam line within half a millimeter.
Oh, I see. Half a millimeter. Okay. That's how close do you have to get the final product?
That's it.
Half a millimeter.
I believe so. I want to say that there might go to a millimeter, but we build it to less than half a millimeter in here.
Yeah, that way you make sure.
Because that way later on down the line, if something happens with regards to the overall positioning and the build out of the structure.
Right. Okay.
15. We got 15 blankets on the inner, and we have 60 blankets on the 50K shield. So the 2K circuit's got 15 layers, and the thermal shield's got 60. Okay, so the way the assembly process works, we get a cavity string that is supported. We essentially build out the cold mass, which includes the magnetic shielding, the instrumentation, the tuners, and the MLI, multi-layer insulation. Then essentially we build the space frame around it. And at that point in time, the whole structure is supported by the space frame at its quarter point. We have tooling that supports it at its quarter points.
Quarter points.
Where the saddles are.
Oh yeah. Okay, that's what. Yeah.
So essentially, what you want to do is maintain your support structure throughout the assembly process. Once the space frame is supported at its quarter points, that's when we do our alignment.
Okay.
So we align it to the space frame on its current support structure.
Okay.
And then essentially, we have the thermal shield put in, the secondary MLI, which is the 60 layers around the 50K shield. Then we build out to the space frame, and then there's another outer warm magnetic shielding we put on again. So we have 2 layers of magnetic shielding.
Oh, okay.
Essentially, that whole component is rolled into the vacuum vessel. Again, the space frame is on wheels, supported at the quarter points. And essentially, we have a track structure inside of the vacuum vessel that those wheels track.
Oh, I see.
Track all the way through to get to that point. But you maintain your quarter point support structure.
And then you
You can see it right there. There's the track.
That's
the
right.
wheels follow.
Oh yeah, that's right. Oh, that's cool.